So hi everyone, welcome to our Monday discussion session. So today I'm going to talk about, I'm going to make a brief talk about the Unit 10. So Unit 10 is talking about the distributed data store. So for this discussion, I will show you three samples about the Quorum protocol and explain why we use this Quorum protocol and how we use this Quorum protocol. So before I start our talk, I want to mention something that because we have finished our project A, and if you're still using your instance on your JetStream, please stop your instance, because if you run your instance on the JetStream, and it still consume a lot of resources on your location.
Oh, right, but I mean, like, are there any, like, that we think are?
Can you mute you?
Basically, I'm going to try to use WildTouch to amplify the templates for the customer. So if we have some, I'll use that.
If you have any questions, you can post on the chat. So, and yeah. So here, so let's start our discussion. So for the Unit 10, we just talk about the distributed data store. It can be named as the DFS, distributed file system. So for the distributed data store and computer network, so distributed data store is a computer network where information is stored on more than one node. So it means that in this system, there are more than one node to host everything. So for example, Amazon just save information in different nodes to make sure that if there's a crash, this crash machine won't affect the server running. So if for example, if Amazon just put everything in a single node and this node is crashed, so everything is gone. So I think it's not a good idea for Amazon to host his servers. So just use the distributed data store or the DFS, distributed file system. So this system could help Amazon to balance the performance and the data store. So here, but in the user or customer side, they just see there's only one machine. But in the server side, there are thousands of machines in it, and the system manages these thousands of nodes or machines to do their work. So there are two important things in this DFS or distributed data store: the data consistency and the data availability. So for the data availability, it means ensure the data continues to be available at a required level of performance. It means, so because there are thousands of nodes in the system, and if one node is crashed, everything in that node is gone. But the system have to make sure the users could still access the same information or same data in this system. So it means some replications are saved in other machine. So to make sure the data won't be lost. Also, the data consistency. So the data would be constant in time and for use to be capable of using and showing them in different ways without changing their structure. It means in our system, because we put a file, we save a file in the distributed data store, and there are thousands of nodes in this system. We save one file in this system means we are going to save this file in different machine or in different nodes to make sure the data is availability. But if someone is going to update data, it means there's a new version of data or there's a new version of file in the system. So the system is going to manage this version update. So it looks like we update something there. So it means like a user update a file into the system, and the system should supply the new version file to the customers, even though it still keeps the old version. But at the read request, the system should supply the new version to the user. So there are one question. Yes, you are right. So here, there are two basic operations in this distributed data store. So one is the read and one is the write. The read operation is very simple, just read. So the system, so the user or the client or the customer just send a read request to the server, and the server just get the data from the node. So it can get data from all node, like this picture. So the server can read data from all node, or it can read data from one node or several nodes. So that's a very basic operation. So about the write one, so write one is a little bit complicated. So like the user sends the write request and update the file into the system. The server will update the file into the entire node or several nodes in it. But the file in this machine, I mean, the user is going to write something in the file, and the file is updated, and the system is going to update the file in one machine, and the machine have to contain a new version of it. So before we implement the write request, the machine only contains the version 1. But when the system finishes the writing request or writing process, then a new version will be saved into the machine. And for this machine, it only keeps the new version, and the old version is gone. So we have to balance the write and read work. Because for the one single node, maybe the write and read work will be very, we will have few write and read work. But for these thousands of nodes about this distributed data store, there may be more than hundreds of thousands requests there. So we have to balance read and write work. So one thing is there are 4 situations there. So first one is the write to all nodes. So if you choose writing to all nodes, there will be heavy write operations there. So like every time the machine is going to write to every node. So it take a lot of work and a lot of cost. Or write to a few nodes. But if you write to a few nodes, like you just write to one node or 2 nodes of thousands of nodes in the system, it cannot guarantee the data consistency. Because if we have thousands of nodes there, we just update to 1 or 2 machines. When the user or when server try to read some data, it cannot find the new version. Also, if we just read from all nodes, it will have read operations. So it will cost a lot of time to load data or to access the server. And but if we read from few nodes, so also same questions. So like our write to few nodes there. So if we read from few nodes, we cannot guarantee the data consistency, because even though we write, so for example, there are maybe 100 data nodes in our system, and the system decide to update 60 nodes in it. But if we just read 1 or 2 nodes to get the data, it cannot guarantee the data consistency. Like it will get the old version from it. So it's not a good idea to do these four cases. 4 choices or decisions on the distributed system. But there are 2 special cases I will discuss later, and how we use these 2 special cases. So here, if you watch the videos, and you will know about the quorum protocol. This quorum protocol is going to balance the read and write work in the distributed data store. So here, when a user wants to read a data object, and the data object is not replicated across every server or every node in distributed data storage system, how does the system know which of these servers or nodes have an up-to-date copy of the data object? So we have these questions about we have this issue in the distributed data storage system, and they develop a quorum protocol to solve it. So the quorum protocol uses voting to figure out which node has up-to-date data object. So here, the basic idea of quorum protocol is require client to request and accurate permission of multi-servers before either reading or writing replicated data items. It means, so the client side are going to send the request or send the read or the write request to the server side. And the server side is going to send the request to the specified nodes in the system, and the system going to accept or reject it. So it's quite easy to understand. So go to next step. So algorithm behavior during write. So consider data store and data object replicate on n servers. So there are n node, n servers in the system. So the rule, to update an object, a client must first contact at least half n servers plus one. So make sure you understand, you remember this one. A client must first contact at least half n servers plus one. So it's very important. And the server get them to agree to do the update. Once they have agreed, the object is changed and new version number. So when the update, the write is done, a new version of files will be saved in the system. So that's why a new version number is associated with the object. And the version number is used to identify the version of the object, and is the same for all newly updated objects. So if the node or if the system just finished the write request, and the machine who accepts the write request have the new version. Still, so for the entire system, even though some nodes keep the old versions, but for the entire system, so user can only access the new version, though it cannot access the old version. So the algorithm, then the next algorithm behavior. So algorithm behavior during read. So to read a replicate data object, a client must also contact at least half and server plus half the server plus one. So it's still, make sure you know that. So the client must contact at least half and servers plus one. So we will discuss it later. And ask them to send the version numbers associated with the object. If all versions number agree, this must be the most recent version, because an attempt to update only the remaining server would fail because there were not enough of them. So that means on the server side, on the distributed file system, so the server will access the amount of node to get the files. And most of them are the new version, most of them are the older version. But the system will consider about this version problem and find which file is the new version and send this new version to the users. So there's no conflict about version problem, because the system just handles this version and send the new version to the customers. So let's go to the definitions of the Quorum protocol. Okay, one question. Okay, no question. Okay, so the definition of the Quorum protocol. So first, we should know the N. The N means the number of nodes that store replicas of the data object. So the N still means the number of nodes in the system. And the NW means the number of replicas that need to acknowledge the receipt of the update before the update complete. So we get the easy definition for about the NW. NW means the number of write nodes. Also, so NR should be the number of replicas that are contact to one data object is accessed through a read operation. So NR could be the number of read node. So here, so this is a very important part about the Quorum protocol. This is the constraints about the Quorum protocols. So first, we know the first one is first constraint is going to prevent read-write conflicts. So number of read and number of read node and cost number of write. First, number of write node plus the number of read node should be larger than the number of node. And the second constraint is going to prevent the write-write conflicts. So the number of write node should be larger than number of node over 2. Why we have these two constraints there? So because first we think about, we are going to balance the read and write operations there. So if we say we just use half means half node 2. So every time the system do the write or read request, it will choose half of node to do it. So it means when the server just do the read request, it will choose half of node to finish the read. And if the server is going to do the write request, it will choose half of node to do the write request. So there's a problem. So if we say the NW equal to N over 2, what will happen? So there's a situation will happen. So first, the system just choose. So it means there are two nodes in the. We suppose there are 2 nodes in the distributed data store system. And when the system do the write work, it chooses the node 1 to write. And then when the system is going to do the write operation, it will choose node 2 to do the write process. And at the end, there are 2 versions. There are 2 versions in the system. The version 1 contains the version 0, and the node 1 contains the version 0, and the node 2 contains the version 1. So at the third step, the machine is going to read the data again, but it still read from the node 1. So the machine will read the old version from the system and send it to the user. So to make a version problem about the entire system, so we make NW. NW means the node of write. Number of write node should be larger than N over 2. So it's going to keep the version, keep the new version in the system, and make sure when we read the entire system, we can get the new version from it. So the further constraint should be the NR should be larger than N over 2. So that's the normal constraints for the Quorum protocol. But so I say that in the beginning there. So one question. So it's not about so Professor didn't mention it in the videos. So when you combine this when you combine the first constraint and the second constraint, you will get this the third one, right?
No, I don't think that's true. I mean, if you have a high number of writers, you could have less than half being readers and still have a valid configuration. Mm-hmm. Correct?
Yeah. So
like if you had N is 10 and you had 8 writers and 2 or 8 writers and 3 readers, let's say, wouldn't that be valid? And the readers would not be greater than N divided by 2.
So yeah, that's a good question. So hold on, so we can think about this part. So if I make a wrong consideration about this one. So yeah, you point out a good question about this one. So I will consider about this. Thank you.
Okay, thanks you.
So yeah, this is a good point about this one. Did I make a wrong further constraints about this, or did I make the right one? So we will consider about this one when I show the examples here. So here, so let's go to our examples. So first, I will say we will set up machines. We will set up a system here. So there's 5 machines in the system. There are 5 machines in system, so we named it as the A, B, C, D, E. There are 5 nodes in it, and so we give the information that the number of write nodes should be 3 and number of read nodes should be 3. So here there are 3 steps. So first one, we'll read data from A, from B, from C. And then the server then write data into C, D, E. And again, at the end, the machine will read the data from A, B, C. So here I just give you the result about this one because that's the easiest one. So first, we know we have 3 write and 3 read. So the first step is the first step is read data from the machine ABC. So we just read the information, the version 0 from A, from B, from C, and show this version 0 to the customer. Then the machine gets the request to update the file. And the server just choose machine C and machine D and machine E to update the information. So here at this part, we can find the server just updates the version 1 to the machine C, D, E. So for right now, when the server just finished the write process, the system will contain 2 versions of data. So the AB will contain version 0 and the CDE will contain the version 1. So the third step, the machine is going to read data again from this system. And it just read from the ABC again. So at that time, the server have 2 versions. So the AB gives the version 0 and C gives the version 1. So the machine will the system will decide to choose the new version, the version 1, and show this version 1 to the users. So here, let's go to the example 2. So first, we set up the environment. Still, we have 5 nodes there, and we have this information, this number of write node and number of read node. So the number of write node should be 3, and number of read node should be 2. So, student, do you think this setup is correct? So go back to our constraints. So ignore the third one. Just ignore the third one. So go back to our constraints. The number of write and number of read nodes should be larger than n, and the number of write nodes should be larger than n over 2. So go back to example 2. So we find the number of write and plus the number of read node is equal to 5. So it's got wrong about the first constraints. So, but we still keep using this system because based on some maybe based on some problem, the developer just set up this environment, even though he think this environment this system is wrong, but it still keep working on it. So what will happen on this setup? So first step, we just read the information from the A and B machine, and we write the files into machine C, D, E. Also, as the third step, the server just read the information from A and C. So what will happen if we just read from A and C? So if you know the answers, just post on the chat, and everyone can start discuss about this one. So yeah, so because we know the system just update information on the CDE machines. So, and it reads from the C, especially the C machine. So the system will got 2 versions. A will give the version 0 and C will give the version 1. But the system will choose the new version, the version 1, and send this version to the customers. So there's no question about that. So what happens if we do this alternative step? So it's just a read from A and B. what will happen? So yeah, because we know there's no update happen on the machine A and B. We just finished the updating work on the machine C, D, E. So if we read from the machine A and B, still gets the old version. So here, this is a graphic about how this one works. So first, we have 5 machines here, and so for the first step, just read it. So it gets the new old version, version 0, to the customer. And when the server do the write request, so it's just the update information on machine C, on machine D, and machine E. So machine C, D, E will get the new version 1 on this machine. So first, when we read the data from machine A and machine C, so we will get 2 different versions, version 0 and version 1. Also, the system will choose the version 1 and send the version 1 to the customer. So there's no version problem about this system. But so something will happen if we choose read from the A and B at the third step. So system just choose the A and B and read the information from A and B. So A and B only contains the old version, version 0. And then when the machine just read the data from these 2 machines and just say, okay, I only find the old version, I only find the version 0. So system will think it's the new version and send this new version to the customer. And the customer will find there's an issue there because, so he said, I just updated this file 1 minute ago, but why still send this old version to me? So for this system, there's a very important issue here about the design of the system. So one student asked questions about if the C crash after towards update A and B were able to read only version is yes still. So there's no connection between this A, B, C, D, E. So I think these machines only keep these individual files and never share its files to other machines. But also, these 5 machines have the basic versions, but it won't share the new version files to each of the system. So when one machine is crashed, it will affect the entire system, but it will affect this version part. So still don't pay too many attention about this exam 2 because this exam 2 has a very terrible issue on the setup because this machine didn't follow the constraints, these 2 constraints here. So let's go to the example 3. So example 3 is more difficult about the DSD distributed data store. So here we still have to think about we have the file node here, and so we think about number of write should be 4 and number of read node should be 2. So go back to our constraints, the further constraints. I think that I make a wrong thing here. So thank you for pointing out this issue on my node here. So where is it? So here, let's go back to our constraint. So this further constraint is wrong. We cannot apply the math function upon these 2 constraints. And the example 3 can show us why we cannot apply just the math function into the constraints. So let's go to see the here, example 3. So I think a student could take a paper and write something on it because it's hard to remember all these steps. So right now we have 5 nodes in the system, and the number of write should be 4 and number of read should be 2. So here, So we have 3 clients here. In the 3 clients to request the access or to request the data information, to request the write or read operation in the system. So the client 1 should read data to read the file from A and B machine. But when client 1 finishes the reading operation and will write new information into the files, and this files will save to the machine A, B, C, and D. So the client 1 finished his work, and the client 2 start to do his work, and he just read data from A and D. And when he got the data there, and he trying to make some updates on these files, and he just sent his updates, and the system just choose B, C, D, and E machines to implement this version update. So it means B, C, D has a new version. So when this step 4 is done, and the client 3 is coming to join this system, and he doing his request. So the client 3 just do read the request, just send the read to the machine, to the system, and the system choose machine A and machine B to check the version and send the result to the customer. Still, so the clients after finishes step 5 and the system, the customer still want to read information again, and at this time the system just choose the data from different node. So he just choose the data from node D and node E. So let's see what will happen if we follow these steps. So here is the graphic to show the steps here. So now we have the same thing, 5 machines contains the data there. And so the steps, client 1 will read the data from machine A and machine B. So this is the first request. So here, so first, the version 0 information will send to the customer. And customer just see the version 0 information. And the customer 1 will update the information to the ABCD. So here, so ABCD will have the new version 1. So, and when the client 1 finishes work and just leave, and client 2 join the system and send his request. The client 2 want to read the data, and the system just choose the data from the machine A and from the machine D. So the client 2 just get this new version 1, and there's no question about the version problem. So client 2 just finish his reading work and try to write something on this file. So he just updates the files, and the system just create a new version to replace the old version. So machine B, C, D, E will keep the version 2 on its disk or on its somewhere. And so go back to, and the client 3 joins the system after client 2 finishes his work. And here, so first, client 2 is going to read, client's going to read the data, and the system just choose data from A and B. So here, from A and B will send the version, A will send the version 1, and the B will send the version 2. So the system will choose the version 2 because this is the new version, and it will send that version to the customer, and customer say, okay, that's the new version. So because, and this is the new version in the entire system. So there's no question about the version part and about the old version. So if the system choose any other two machines, like choose the machine D and E, so also the D will give the version 2 and the D will give the version E. So we find the new version 2 in the system, and the customer will see the new version 2. So here, right now in our system, go back to our step 2, the right part, this part. So the right part here, we can see we just the number of write nodes should be 4. So here in this step, 4 node will update the information. Seems like these 4 machines will contain a new version, and only one the machine A at this step, machine A will keep the older version. So as we know, the number. Hold on, go back to our setup part. So here. So as we know, the number of read nodes should be 2. So even though at this step, the only one machine contains the older version, and there's no trouble. I mean, there's no conflict about the version part, because only one machine contains the older version, and the other machines contains the new version. So we have to choose we have to choose 2 of node from this system. So there's no older. So even though we choose A, but we will choose any other one machine from this 4 node, and the system still will get the new version files. So yeah, so this example can say the further constraint is wrong, because we can show this very clear example. So, but so it's I got these 2 special cases in the distributed file system, and it doesn't follow the constraint. So let's go to our 2 special cases. So here, the first one is the number of write nodes should be 1, and the number of write nodes should be the n. So this is the case that the system have heavy reading requests from client. So like the library, so maybe students, hundreds of thousands of students just send the reading request, and the server have to handle this request. So if we just say we will keep more than one node to do we will use more than one node to implement the reading request. This will be a heavy reading task, or it will cost a lot of time, because there are thousands of requests there. But here, we just let the system choose one node to process the read request. Why we can do that? Because here we ask every node to update the information when the library side just updated the fork to the library storage, and each node in this system should update the information. So based on this case, the old node contains the new version. There's no old version in this system. So even though we just use one node even though the system just request one node to send the file, to read the file, but they will get the new version about the files. Then there's no conflict about the version problem. So, but about the case 2, we have so the number of read nodes should be n, and the number of write nodes should be 1. So in this case, because of we have the hold on. So I cannot get the chat room. So here we just so why we choose this system? Because we have the heavy writing request from client. So what's that mean? Heavy writing request. So means like hundreds of thousands just try to access a file. Like we use Google Doc, right? Like kind of Google Doc. So hundreds of thousands to try to update the information. one by one. So even though because we know there's a block there, so no one can access the same machine can access the same file in that same machine at the same time. There's a block, even though there's a block. But right now we ignore this block, and so it means every second the the files is going to update by thousands of students, by a student, and but there are only few students going. There are few of students just going to read it. They just update the information to update the notes there, and now only few of students just read it. So we just reduce the writing work, reduce the writing task, and so it can take easy work about the writing, and we just use this work, use all node to read the information to get the new version. So it will balance the write and read work in this system. So okay, so I think this is a very good special case about our distributed file system, and why the system cannot follow, why this kind of two system cannot, this is case 2 cannot follow the constraints. So there's no question about case 1, because we think so the case 1 is good because we find the further constraints is wrong, because it's not a good conclusion from these two constraints. But this case 2, so this case 2 give a good sample, a special sample about why we don't want to follow it, because we have to develop a system for some special case, and we cannot follow everything. By using these constraints, and we just want to make their work. We want to improve the performance of the system. So can anyone give more examples about case 2? Because my example is it's very limited. So can anyone share his experience about the case 2? Have you ever get this system, this case 2 system? So I think it's in the world, there are few systems have this setup, because people pay attention about the result, and hold on. So what will happen? This one. So there's a problem here. So when that node is crashed, so they cannot get the new version. So that's a problem about this system. So like the client just update a new file into the machine 1, and at that time machine 1 is crashed. But at that moment, the customer trying to read the information, and the system only can get the old version and version 0 from it, and so there's an issue here. So here, this case is very special. So we should think more about this part, how to handle the crash case and how to handle the work balance. So yeah. So we have a good discussion on our chat. So you see that we add additional write node. What will happen if these two nodes crash? So yeah, this is some case, just some special case. So we can think about this one. But right now I cannot find any examples about this case too, because there are a lot of issues about this case, how to handle the crash problem, how to handle the data consistency. So the case 2 is a good case to discuss on the Piazza thread, and everyone can share his ideas about this case 2.
I think that that case 2
Mm-hmm.
Useful when you are writing heavily to a transaction log of some sort.
Mm-hmm.
If there are many transactions that are happening, but the log is only read from occasionally, you might want to split those writes up. Rather than trying to write to a single location, you might distribute those writes into many different nodes. But then when someone would want to come along later and understand, for example, what a particular client or what a particular piece of data, what kind of activity it had experienced in the transactions, they would have to read from all the nodes in order to get a consistent view.
Yeah, that's a good idea. So I think we have the same discussion on our hotel data, right?
Yes, very much so.
Yeah. Okay, thank you for your point out. It's a good idea. Okay, thank you. So, okay, everyone. So I think I have finished the discussion. It's 5:46. So I have to end this one and start the next session. So one question is during I write to the. Believe the inconsistent if one of the. Yeah, that's correct. So it's very hard to maintain. It's hard to make the data consistency and data availability. So that's still a question. That's still a problem for the entire distributed file system.
All right, absolutely. So I just think it's worth pointing out that a lot of the scenarios that we've been working with assume that everything is going to work the way it's supposed to when writes are happening. And that may not be the case. And therefore, in order to maintain consistency, you have to do more than just write to a certain number of nodes. You also have to make sure that those writes all succeed. And to do that, you might require a special kind of transactional management, which can be very expensive to run in a highly distributed and very busy system. And that's why eventual consistency, which doesn't require that kind of transaction management, has become so popular in big data scenarios.
Thank you, Chris. Thank you for pointing out this one. So, okay, everyone. So I have to stop this discussion, and I think I have to start another one. So if you have any questions about this homework or this section, you can post on the Piazza, and I think it's a good time for us to discuss there. Also, we are discussing about our next project. We were still thinking about this one, and I think we can discuss in next Monday's discussion. And I think at next week, we can let you know what you should do for the project B. So just wait there. So yeah, I think this project won't be very difficult. It will be easier than the project A, because based on our, crashing from the project A, we find there are a lot of questions there. So we are going to balance the work and make sure everyone can learn something from the project. Okay, thank you everyone. So I have to stop here. So I'm going to start the next one. And I'm going to fix the slide error. There's no further constraints here. Okay, thank you. Thank you to point out my mistake. Okay, bye.